This lecture is going to take you through two real important concepts that are covered in Chapter 21, the hemodynamics chapter of cardiovascular system. The first is capillary fluid exchange, and the second will be mean arterial pressure. Before we look at that image of capillary fluid exchange that shows those forces in that process of what's happening at the capillary beds, I've got two terms I need to take you through. First is the term hydrostatic pressure. You need to understand that when we refer to hydrostatic pressure, it's a push pressure. It's a force that's actually generated either by the pumping of the blood, basically that pumping of the heart, and then the actual total volume of blood, the pressure of the fluid against those capillary walls, or actually against any blood vessel wall, but since we're dealing with fluid exchange, we're specifically looking at a capillary bed. But hydrostatic pressure is the pressure you actually measure when you do blood pressure. It's measured in millimeters of mercury, and it's a push pressure that's generated as a force through the blood vessels that's generated by that pumping of the heart, that pushing of the blood through the blood vessels, and it can increase with the greater the blood pressure, the greater the volume of blood. An increase in blood pressure, increase in blood volume, increases hydrostatic pressure. So again, think of how the capillary wall may be stretched as the volume increases and pushes against that capillary wall. You're going to see that push of fluid through that capillary wall. The second concept is osmotic pressure. And osmotic pressure is a pull pressure. It's generated by the solute, whatever that solute may be. And what we're going to be looking at with capillary fluid exchange, the main solute we're dealing with is albumin. Albumin is that plasma protein that's produced in the liver. And it's the smallest of the plasma proteins, but it's the most abundant. When we start talking about things like osmotic pressure is generated by the number of solute, not the size of the solute. So, for instance, if I were to, comparatively speaking, if I had two fluids side by side in a container separated by a membrane, so if I would think of a tube with fluid in it, I slide a membrane between them, and I put sand on one side drop sand particles in on one side that weigh a gram. The water from the side without the sand will be pulled towards the side with the sand in an attempt to try and get to an isotonic or equal status in which the amount of solute equals a ratio of solute to water is equal. However, if instead of sand I would just I put sand on one side, so I have a million particles of sand on one side that weigh a gram, and then I take one stone that weighs 10 grams and put it on the other side, that will have actually very little, if any, movement of water at all. Now, it might displace the water, and the volume might rise a little bit, but you won't actually see a net movement of water to try and fix that ratio, because the ratio is one particle. It may weigh 5 grams, but nothing compared to the million particles of sand that pull. So osmotic pressure is generated by the number of particles, not the size of the particles. So albumin is small but abundant. So that pressure that's generated pulls the water or the fluid towards it across the membrane. So here's the image that we need to look at. This is the image that you have in your textbook. Recall what we're looking at is just a small segment of a capillary representing a full capillary bed. So you understand it's a meshwork of many, many vessels, but we're just looking at a small piece to make sense out of it. And so what we have is blood's flowing into it here on the red, where the red is on the left side. Oxygenated blood is entering into the capillary bed here. It's being propelled or pushed by the pumping of the heart through the capillary bed out to the venous end, and then we'll go from the venous end into the venules, and then eventually back into the vena cavas and back to the lungs. Back to the heart and eventually through the lungs, and where it will pick up its oxygen. So that's the concept that we have here. This represents the tissue cell. So capillaries exist to bring oxygen and nutrients and pick up carbon dioxide and waste from our tissues. And wherever we have capillaries in most areas of the body, you will also find lymphatic vessels. We'll talk about lymphatic vessels in the next chapter, but these vessels function to help with fluid balance. So I'll talk briefly about them here and a lot more about them when we get into the lymphatic chapter. So what you have going on here then are measures of hydrostatic and osmotic pressures. So the key over here lists the four main pressures, and then the net filtration pressure is the balance at the end that we can calculate. So there's technically four pressures at work here. You have two hydrostatic pressures and two osmotic pressures. So two pushes and two pulls. So if we take a look at first what's happening really from the perspective of the capillary itself, as the blood enters in and flows through here based on the volume and pressure of that blood, pushes against this capillary wall and promotes the movement of fluid out of the blood vessel. That's the blood hydrostatic pressure. So there's a force at work that's promoting fluid movement this way. Likewise, at the same exact time, there's an opposing force that's generated by that albumin that we call the blood colloid osmotic pressure. Remember, colloid is something that does not dissolve, so that albumin does not break down or dissociate, it stays as albumin. So these two forces are really opposing each other, but what they're doing is one's a push out and one's a pull back in. You see here at the arterial end that the blood pressure is still fairly high. It's at 35. This is the force generated by the heart. By the time we get to the capillary bed, it may have been about 120 or so when we left the heart right at the aorta. But as you get to the capillary bed and all that branching that's gone on, the pressure drops. With every time a vessel branches, the pressure within that vessel drops. So I always want to think about it sort of like as a garden hose. If I take a single hose, attach it to a spigot at my house and turn it on to sprinkle my lawn, I'll have pretty good force coming off that single hose, especially if it's not too long. But if I take and put little Y pieces in it and say, well, I'm going to run a sprinkler system and I'm going to water 12 different flower beds, well, the pressure that will exist at each one of those spigot ends, if there's 12 ends coming off a single hose, may not be enough to even generate the spray necessary to water the flowers, because the pressure drops as you branch. So this is what's happening here in a capillary bed. The pressure drops as you branch your way through those capillaries. So we're down to 35 millimeters when we enter in. This is a capillary bed, not a single vessel that we're thinking about here. And so it's all branching its way through the area around the tissues, so that when we get to the venous end, the blood hydrostatic pressure has gone from 35 to 16. It's important to note that there's going to be a significant drop with the branching. You don't have to have any of these numbers memorized at all. You just have to understand the concepts and the equation, but no specific numbers. So the blood colloid osmotic pressure should not change. If the vessel's healthy and nothing unusual is going on, this blood colloid osmotic pressure stays the same all the way through. Rest assured, there are certainly diseases, there's inflammation and problems that can occur that can change this factor, but for AMP2 purposes, we assume all things stay normal and this value stays the same throughout the capillary bed. We do not see really a change in the blood colloid osmotic pressure because we don't lose albumin in any significant amount under normal healthy conditions. So what we have happening here is we have this force at the arterial end that tends to be greater with the push of fluid out, which means some fluid does leave the vessel. And we need that fluid. It helps for nutrients to migrate across this interstitial space, which again, here looks awfully large. It's nanometers to millimeters in distance. But nonetheless, when you blow it up like we're looking at here, there is space for nutrients to move, and you need a fluid in here. This fluid that we find, this interstitial fluid around our vessels and tissues, is really in a more or less gel-like form. You're not all sloshy and watery truly in between there, but you need fluid to help move through that tissue gel-like substance that makes up our interstitial fluid, so we can get the oxygen to the tissues, and likewise the carbon dioxide can migrate back the other way. So knowing that some fluid gets out here, we promote it at the arterial end, but really as we move through the area to the venous end, you see that then the pressure goes the other way. There's actually a force that is greater pulling in than pushing out, so we regain much of the fluid. What we normally need to do, though, is take a look at all the concepts or all of the factors that figure in. So we've just looked here in the vessel. It changes as we move through the vessel, but nonetheless, we are definitely going to have some movement of fluid out and then movement back in. The two other factors that affect blood or capillary fluid exchange are more theoretical in terms of the normal function and don't play a big impact even at a disease process state in most cases. But you need to recognize that the potential for these forces exists. The first is interstitial fluid osmotic pressure. So it's a pull, but it's a pull out of the vessel. Blood colloid osmotic pressure pulled the fluid into the vessel. This is generated by solutes that are sitting out here in the interstitial space. This can be generated by a little bit of the albumin that might leak out, so that may be part of it. Some sodium may be part of it, although sodium likes to hang around at the cells, so it's not really in this area as much. But sodium is certainly osmotically active, so there may be a little bit of a pull force, especially if the sodium levels start to rise. And things like glucose can also be responsible for, and there are some other proteins that can maybe have an osmotic capability of pulling some fluid out. So this it's given a 1 in our equation here. It is theoretically a value that may exist and be even greater than that, particularly if you have some damage to the capillary and now you've got albumin seeping out here, that could increase. Interstitial fluid hydrostatic pressure is a push pressure generated by the fluid outside here. And under normal circumstances, that should be 0. The volume of fluid, that tissue gel out here, should really not have an impact pushing them back in. However, if fluid does start to accumulate out here, you start to get an edema issue going on and there's an excess of fluid in this space, there may be a force where it's literally the weight of the fluid pushing back on the vessel that may push some fluid back in. Even then, the amount is minimal. It's certainly not going to come anywhere near what we see going on inside the capillary, but it's worth noting that it exists. So, how do you calculate this? What you need to do is determine net filtration pressure. Now, our formulas here give you a net filtration at the arterial end and a net filtration, really what they refer to as a reabsorption, but really it's what's the net filtration. It's more of a reabsorption than it's more in than out, but it's really the exact same formula. What you do, so it's a little tricky. At the bottom, these two boxes show arterial and venous end, and it's the full equation. But right in here, right in here where it says net filtration pressure, this is the full equation. This isn't just arterial end or venous end. This is the full thing. And so you can see down here there's two sets of numbers. So what you do is what factors promote the movement of fluid out or filtration out, and what factors promote the reabsorption or the holding in or pulling in of the fluid. So you've got a blood hydrostatic pressure, an arrow out, and then you've got an interstitial fluid osmotic pressure, which is a pull out. So you've got a pull out interstitial fluid osmotic pressure, pulls it out right here, and blood hydrostatic pressure pushes it out. So you've got two outs. These two arrows here are the factors or pressures that promote filtration. And you take those two and you subtract that. Actually, it's interesting. That minus sign should be pretty much down in here. You then actually subtract, you add those two values, the two forces that move fluid out, the two arrows that move fluid out, one's a push out, one's a pull out, and subtract from that the two arrows in. And so we've got a blood colloid osmotic pressure, and we've got our interstitial fluid osmotic pressure. Interstitial fluid hydrostatic pressure. These two pressures promote in. Now I realize that there aren't 4 arrows here. There are 6 arrows in the picture. Remember, these final 2 arrows are simply repeats of these ones right here, showing how it changes from arterial to venous end. But in terms of the four measurements that you need to calculate net filtration, it's these first 4 arrows. This one, this one, this one, and this one. So what forces promote fluid out? A push out and a pull out by the interstitial fluid. What forces favor keeping fluid in or reabsorbing it back in? A blood colloid osmotic pressure, a pull in, and an interstitial fluid hydrostatic pressure, a push in. Again, usually this one is 0. So how do you calculate that? If you just look at this first box here, you take the 35 bhp plus the interstitial fluid osmotic pressure, which was 1. That gives you 36. You subtract from that the blood colloid osmotic pressure, which is 26, no matter which end you're in, plus the interstitial fluid hydrostatic pressure, which is usually 0. You add those two together and you find the difference. So at the arterial end, we have a net filtration of 10 millimeters of mercury. If we work our way through, we actually wind up with a negative number, same exact formula. And so what we're saying is the pressure is not forcing out, but rather a pull back in. It actually is a reabsorption pressure. Still net filtration, it's just a negative number. And so it really is promoting reabsorption. So the difference between the two is a net 1 millimeter of mercury. What that basically tells you is that the forces moving out are slightly greater. Remember, this is a measurement of pressure, not volume. The forces that move fluid out are slightly greater than the forces holding the fluid or reabsorbing the fluid back in, because the difference between the two favors, it's a positive number, so it favors the movement of fluid out. That means at a capillary bed, under normal healthy circumstances, the net filtration pressure is such that it promotes a little bit of excess fluid being lost from the blood vessels, lost from the capillaries as blood is flowing through. And that's where your lymphatic vessel comes in. That lymphatic vessel is capable of reabsorbing that excess fluid because of that 1 millimeter pressure of fluids moving out. Lymphatic vessels pick up the excess fluid. They actually work their way into these vessels, and then that takes it, it says right here, lymphatic vessels returns to the blood plasma. It actually flows back in right up there at the superior vena cava and the brachiocephalic veins. It joins right in there, and lymphatic vessel deposits its excess fluid back into the blood supply, so you actually maintain blood volume. So we'll talk more about that lymphatic vessel in the next chapter. I just need you to know that the net filtration pressure under normal circumstances does promote a little excess fluid leaving the capillaries as blood's flowing through there, picked up by lymphatic vessels, put back in the blood supply, so we actually don't see a drop in blood volume. The net blood volume should stay the same as long as your lymphatic vessels are healthy. So let's look at one of these problems. If I give you blood hydrostatic pressure, sometimes referred to as capillary hydrostatic pressure, I give you a value as 30. Blood colloid osmotic pressure is 28. Interstitial fluid hydrostatic pressure, sometimes just IHP, you might see it, is 1 millimeter mercury. And interstitial fluid osmotic pressure, sometimes listed as ICOP, is 1 millimeter of mercury. So what's the net filtration pressure? Which two forces are promoting fluid out? Add those two together. Which two forces are promoting the reabsorption in? Add those together and find the difference. And so your answer is, you take the 30 of blood hydrostatic pressure, you take the 1 from interstitial fluid osmotic pressure, because remember that's a pull out, you add those two together, subtract from the blood colloid osmotic pressure plus the interstitial fluid hydrostatic pressure, which comes to 29, and you find a net difference of 2 millimeters of mercury. This is only slightly greater than what was the first example we looked at. So lymphatic vessels certainly going to be able to manage that, and you will not have edema forming. If these numbers had been different, if the blood hydrostatic pressure had been 40 instead of 30, then the difference would have been 12 millimeters of mercury. That would have been far greater than the two, and would have said, well, gosh, that's a fluid overload. More fluid, the lymphatic vessel can't pick up that kind of volume, and you start to have excess fluid accumulating in that interstitial space. If we go back here, that would be excess fluid within here, and we would start to have edema forming. We'd have excess fluid in this space, and we'd have that swelling or the edema that forms. So the reason we need you to know this is because when you do get to patho, we go through this again a lot quicker, and we assume you retained it, and we talk then about what mechanisms are actually happening when edema, when excess fluid forms there. How does that affect the functions of the cells? How does that affect fluid and electrolyte balance within the body? So it's real important you get this concept now, because you're certainly going to need it for when you get to patho. All right. The one other concept I just want to introduce to you is this idea of mean arterial pressure. in lab, you're going to measure blood pressure, systolic over diastolic, 120 over 80. Those are the measurements of the force of the blood being pumped through. It really is the high and low pressures, the pressure that when that the ventricles build up to open this aortic semilunar valve and eject the blood up into the aorta, and the pressure at which the blood starts to flow back and that aortic semilunar valve closes. So 120 is the pressure that is generated on a healthy, normal heart, that's generated at the ventricles to open up the valve, pump the blood out, and get enough blood out to meet our needs. And at 80 millimeters of mercury is when the pressure starts dropping back down enough to close the valves off, and that's the pressure you have to at least get to 80 in order to open that valve up. We try and get to 120. That helps pump out adequate amounts of blood. So you're going to look at that at lab. Mean arterial pressure is based on that same concept, but it's the average blood pressure in arteries throughout the body. So it gives a more overarching measurement of how things are going systemically in the blood vessels. Really, your blood pressure, systolic over diastolic, is really a measure of the function of the heart. Mean arterial pressure takes more of a focus on what's happening in the blood vessels as a whole. How are those blood vessels managing with that pumping sensation? Is a normal pressure being maintained? We look a lot at mean arterial pressure when we get to the urinary system. So I want you to understand the concept of it here. I want you to recognize the formula. You will not have to calculate it on this exam. You will calculate it at the final exam when we do the urinary system. So we'll come back to it, but I want you to be familiar with it now. I'm going to show you the calculation, and then we will revisit this again in a few weeks when we get towards the end of the term and we're in the urinary system. So mean arterial pressure and average blood pressure in the arteries throughout the body, and really gives us a better sense of the arterial circulation than just the function of the heart. So there's really two formulas. One we can really calculate, and one's more theoretical. Mean arterial pressure is equal to the cardiac output, which you already know, stroke volume times heart rate, times resistance. And we'll talk more about resistance. It's in the chapter, and you'll get that in the lecture. But resistance refers to things that impede blood flow or prevent blood flow from happening or reduce the effectiveness of blood flow. Anything that blocks a vessel or blocks a part of a vessel causes resistance. So you can look at that as a theoretical measure. Well, we can't easily measure resistance. What are we going to use to measure that? So it's more theoretical than anything. So what instead we use is we take a look at the value of the blood pressure of the body, and we use that to determine mean arterial pressure. The formula is the diastolic blood pressure plus 1/3 systolic minus diastolic. Everybody gets a little freaked out sometimes when they see the 1/3. So I could also have written this as diastolic blood pressure plus systolic minus diastolic divided by 3. So if the 1/3 kind of freaks you out, just remember 1/3 of this value is really this value divided by 3. So sometimes that students feel a little bit better if they don't see that fraction sitting in front of them. It's formulated the same way. So if you've got a blood pressure of 120 over 80, 80 is the diastolic, so that goes in the first spot. It'll be 1/3 of systolic minus diastolic. That's 120 minus 80, which equals 40. And so see, here I've converted it. You have 80 plus, you take the 40 divided by 3. That's 1/3 of 40, is 40 divided by 3. 40 divided by 3 is 13.33, and then the 80 just kept carried down, so that our mean arterial pressure is 93.33. So that's how it's calculated. You will eventually have to calculate it, although this calculation will not be on the exam, but you absolutely have to be familiar with the formula, both of them, because either one may show up as which of these is the correct formula for mean arterial pressure. You don't have to calculate it, but you've got to recognize it. You may even be asked to write it. So be sure you know, and if I ask you to write the formula for mean arterial pressure, I will take either one. You don't need both. I would not ask for both. But I might give you a list of them, and you have to tell me which one's correct. So watch out that you don't get the systolics and diastolics mixed up. And that's it for this lecture. We'll complete the rest of the content in class.